this presentation, I'll describe an interface for live coding on top of an interactive visualization of a sound collection. I'll start by showing a quick example of using the interface. The roots go back to this bit of research that we did a couple of years ago, where we compared different dimensionality reduction algorithms for creating musical interfaces that adapt to distributions of data in a sound collection. So we call them data-driven musical interfaces. And the idea was to use a relatively conventional pipeline where we start doing a short time for retransform, then some feature extraction, optionally using some feature learning. Here we used constructive autoencoder. And then we could do some segmentation using these features, and then each segment is summarized into a data point. And then we try different dimensionality reduction algorithms to map those data points to a two-dimensional space. So then these two-dimensional spaces can be used to visualize the sound collection in different ways. And then we also use an indexing algorithm, here a KD tree, to create a quick index of this space. So using some input device, you can query for a sound in a given position to this space. This was done using an early version of the fluid corpus manipulation toolbox, where we were missing many of the elements needed for this workflow, so some of the boxes here were implemented in Python using several NumPy, particularly Scalern and other Python libraries. And then we used this to create several interfaces that were created mainly in SuperCollider and then with the use of JavaScript for the user interface. So here are some screenshots. The whole workflow was organized around this SuperCollider prototype at the left that we used to create the map to try different dimensionality reduction algorithms and see the shapes that you get and play the sounds with different playback algorithms. And then the interfaces at the right were coded in JavaScript. So they could be used in a multi-touch tablet like an iPad using a web browser, and then they would connect to SuperCollider for playing the sounds. The first one is a scatter plot where we map the collection of sounds to 3 dimensions. The 2 dimensions are the space, and then the 3rd dimension is color. So here each sound is represented by one circle, and then the size is the duration of the sound. So this was played just by touching the screen of the iPad with several fingers. The second one is a multi-touch slider. So here we tried going beyond 2 dimensions, and here actually 4 dimensions. So each of the sliders is a histogram showing the density of data in different parts of the slider. So you could find different positions by moving the sliders and finding a given configuration of the multi-slider, and then you could always know where there was more density of sounds in each of the sliders. The third example is a drum machine. Here we used a self-organizing map to first cluster the sounds into this grid of 16 boxes. Then for each of the boxes we used dimensionality reduction to map the sounds of the box. So they are these kind of white dots. Then the gray square in each box is a 2-dimensional slider that you can use to select the sound for each box. So this could be used like a drum machine where you can make a pattern of the different boxes, and then while the pattern is playing you can select the sound corresponding to each box. So this worked well for doing our research, but the implementation was a bit of a Frankenstein project, where some bits were in SuperCollider, some bits were in Python, and some bits were in JavaScript. So it is not very practical for using in real-world music creation workflows. So I've now been working on a new version using only SuperCollider with the current version of the Fluid Corpus Manipulation Toolbox. The new version is a more modular, object-oriented library written in the SuperCollider language, where some of the objects encapsulate the functionality in the data processing pipeline using the current version of the Fluid Corpus Manipulation library. So this now has roughly the same features as the Python plus SuperCollider plus JavaScript version. And a new feature is the possibility to render each sound as an icon instead of just a dot or a bar. Now we can use a little waveform that represents some audio feature and some color that is also mapped to another feature. But in order to do that, we need to be able to allocate some space to each of the sounds. So here another addition is an algorithm that can assign each of the points obtained from a 2-dimensional space generated with dimensionality reduction algorithms to a grid where the icons can be evenly spaced. So now each of these objects can be configured in different ways. So we can use different features for the position, normally using a high dimension feature like MemCCs or Chroma. Then we can also use a different feature for the icon and for the color, typically using 1-dimensional features like spectral centroid or pitch or loudness. We can then use different dimensionality reduction algorithms for the projection, and we can optionally use the grid. And we can also choose between different slicing algorithms available in the Fluid Corpus Manipulation Toolbox to segment existing recordings into shorter snippets. I'll now demonstrate one example interface that I've been working on using this library that I will use for my performance at the Dialogues Festival in Edinburgh. So this interface is based on a collection of recordings of cooking sounds, sounds of frying, boiling, braising. And the recordings are quite informal and they have some background noise. So the idea is to have a variety of noises that I can process in real time during a performance. The collection is now like 250 recordings. I plan to cut them into pieces, so there will be more in the future. The map is generated from audio analysis, in this case using MFCC features. The MFCCs are projected into 2 dimensions using an algorithm called UMAP. And then the map is snapped to this grid using an algorithm called Jonker-Bolgenand, which is a variant of the Hungarian algorithm. So it's an assignment algorithm that assigns the points to each point in a grid. And of course, this distorts a bit the map generated by the UMAP algorithm. So here I'm using more points in the grid than there are in the original map. So it's kind of an oversampled grid. And so this still approximates the original shape of the map. So in the end, hopefully similar sounds should still be located close together in the grid. And then the icons, the color represents the spectral centroid, so it's still kind of correlated with the position generated with the MCCs, as you can see. And then the waveform is a loudness descriptor. And I'm going to play some sounds. So the blue color usually has higher frequency sounds, and the warmer colors are kind of low frequency sounds. So, and the height of the line is the loudness. So here's some loud, high frequency sounds. Here's some loud, low frequency sounds. Here are some quiet sounds. And here, these have a bit more kind of variety in the recordings. So as you can see, I have this kind of gray circle is a player. It's still a bit buggy, but it's supposed to play the sound that is closest to the position. And this one is associated with a small snippet of super collider code that then has a synthesizer that plays the sound. And I can have up to 8 of these players. And here I'm playing them, I'm moving them with the trackpad of the laptop, but I can also use a multi-touch interface using an iPad as a controller with a software called Touchos, and I can play several of them at the same time. And so the code for this player is I can do it using live coding. So this is an interface that is based on a library that I have for doing this kind of live coding interfaces. And I'm going to start again, but what I have is some symbols that map to different elements of the interface. So here amp.kr represents this slider here, which I'm controlling with a MIDI interface. And then this, I'll use it to multiply a granulator. And here buff.kr represents the sound that is currently selected by the gray dot. I'll play it at half speed, and it's going to play grains from somewhere in the middle. So I'll have like a more stable sound. So I can have several of these. Each one has like a different level of gray, and each one has like an associated gray dot with the same level of gray approximately. So I can use this to sort of decouple the synthesis and playback algorithm from the sound that is currently being selected, right? So I can use another one, for example, with a filter. 100 Hertz, something like this. And this one I can use with lower frequencies, for example. And then I can record some of these trajectories that I'm drawing, so I can kind of automate. So this one was controlling here and record trajectory. Now it starts looping my gesture. And the second one, I'll record another one. I'll do a third one. This one's good. As for next steps, as I mentioned, the idea is to continue to add more sounds to the interface. There are some issues that need to be sorted in the code in order for it to be able to handle larger quantities of icons and sounds, but work is on the way. Beyond that, there are two main directions that I'm exploring for this work. One is the idea of procedural control of the trajectories. So right now I can record a trajectory with either multi-touch or a trackpad, but I'd like to be able to write a function that defines the trajectory. So the idea is to add a code box, and besides the code box that I use for the synthesis, another box that I can use to code a function that will define the trajectory of a player in the space. And of course, this can be extended to patterns and so on. The other general direction that I'm considering is continuing with gestural control. So right now there is a multi-touch interface that works well and it's quite powerful, but it does require some practice to learn how to use it effectively. And then I'm still missing some further controls, like something for zooming and panning in the plot, something for controlling the volumes, and so on. So this is something that I'm planning to continue exploring in the future. So I'll leave it here and thank you for listening.